go to design and click layout. And that's my click layout. It's my favorite one. You know, it's the chart title, it's all this stuff. I think I'll show this again real quick. Look at all these options, got so many cool things, it's so nice.
Gary! I was just looking for the sports channel, Gary.
Hey everybody, how are we doing? It is Wednesday. It's already Wednesday. It's already halfway through the week. So it is time to get to learning here. It's time to go over some material. We've got Stat 201. Currently, we'll be doing a new chapter today, and it's a pretty tough one. So I might cover some 201. We'll see if anyone hops into the chat right here, and they can ask some questions. But I'm going to pull up the 201 assignments because this is some pretty tough stuff. This is, when you think about the hardest chapters on the test, this chapter will be one of the harder chapters. So I'm going to pull up the sampling distribution of the sample proportion right now. We'll see if anyone jumps into the chat here. Hey, Wacky Wednesdays. It's totally Wacky Wednesdays. Hey, Dan. So good to see you. Let me see here. I have Crash on. What do I have as my buttons over here? Let me go over to the main screen, and then I can actually hit the button. Let's do it. Let's hop. What's currently on this button right here? Wait, is it not doing it? Oh, it's not doing it. Working on chapter 12. Do you want some help with chapter 12, Wilson? My button doesn't do anything. My button doesn't, absolutely nothing. I think it's for over here, actually. Let's try it over here. There we go. There's Crash. He's loaded in right now. It's not Throwback Thursdays. It's Wacky Wednesdays. I'm just hopping around screens, doing all this random stuff right here. This is absolute random. Which one are you working on, Wilson? Which problem are you working on? We can take a look at that right here. Let's put down chapter 12 assignments. So feel free to ask a question about which one you're working on. This is all the probability stuff. And probably the most helpful thing for probability is to know this table instantaneously. I'm going to draw this table while we talk. Let's see if I can remember how many rows it has. I think that's it right there. Okay. The first one with the heads and the tails, like I just opened it. Cool, we'll take a look at that. I'm going to write this out really quickly. Let's write out the rule. Let's write out the condition, the sign, and the word. We'll use this a lot. We've got the addition rule. The condition is disjoint. The sign is plus, and the word is or. We've got here the multiplication. Multiplication. There we go. That worked, right? The rule is independent. Rule's independent. The sign is a multiply sign. And the word is and then we have the complement rule. There's really no condition for it. So we just put that. And the sign is 1 minus probability of A. And we say not usually for that. So here are some shorthand things we'll use throughout this. So remember to use this as a resource right here. I'm going to shade the cells. How do you shade cells? Table design. Sure. Let's use that. Oh, cool. Yeah, that's great. That was good. So you can see the different rules right here. Yeah, not too bad. Chapter 13 is just, it's kind of like, I think a lot of people have never heard of chapter 13, like the concepts inside of it, the sampling distribution of the sample proportion and the sampling distribution of the sample mean. They're completely new topics. So it's hard for a lot of times because people have never done those topics. And we'll do this. So it's a really good time. Like, Dan, if you want to take a look at one of the questions, I can show you how to do one of them. And if you understand one of them, you pretty much understand all of them. But the sampling distribution of the sample proportion is, here, we'll talk about this really quick. Let's do chapter 12 to start, and then let's do a sampling distribution of the sample proportion question. Because you need a lot of practice with this chapter. People get to questions on this on the test, and they say, they're just like, I have no idea how to do this. They're just like, well, whatever. They're like, I don't know. And it's just one of those things that someone said, you know, how do you multiply two numbers and you didn't know how to multiply? You'd be like, I have no idea how to multiply. How do I multiply? But once you know how to do it, it's not that bad. So they're very mathematical, and we'll do some of those, and they're really good practice. So if you want to take a look at one of them, feel free to ask Dan. We'll definitely do that because lots of practice. If you practice them and you get to the test, they're super easy. But if you get to the test and you've only done one or two of them, you'll be like, wait, what? What question is this? Hey, what's up, Timothy? So good to see you here. Good to see you. I got my water. Yay, water. Lots of water, feeling good. Always drinking water. So what we have right here is the concept of a sample space. Now, this is different from a sample frame. Okay, would an example of the multiplication rule be something like, what's the probability that Jim gets let out of class and he misses his bus? Bingo, yep. Because I think they use that one. Don't they use that one here? We've got one where you can do that. I know that problem's on here. Let me go look at the quiz real quick, then we'll come back and do this one. I'm gonna be less scatterbrained. So let's open up the quiz here. That would be the multiplication rule. And let's take a look. A lot of similar questions. Wait, is this one it? Yeah, here it is right here. So a student figures out that he has a 72% chance of being let out of class late. If he leaves class late, there is a 25% chance that he will miss his train. Now, the important thing to note right here, and the thing I wanted to point out, is that this is kind of like a conditional probability. So we would say, if this comes true, and then this comes true. So we know the probability he misses his train if he gets out late. So think about this. What are all the scenarios that could happen here? So we've got 72%, 25% chance. And let's go right here. So let's say we have a 72% chance. So probability late class equals 72%. Probability misses train is 25%. Now, the probability of missed train only happens, was it 25%? Sure, get it right. The probability of missing the train only happens if he gets let out of class late. So there's multiple scenarios right here. We could also have the probability of on-time class. We'll say on-time class is 28%. It's the complement of being let out of class late. You're either let out of class late or on time. Like you can say late or not late. So I guess that's the easiest way to do the complement of it. And then we have here probability of not missed train. Now, one key assumption we're going to have to do right here is we're going to have to assume that if he's let out of class not late, he will catch his train. So in all scenarios, if he's not let out of class late, he catches the train, or he's on time for the train. You could say, like, what if the train's late? There's so many scenarios when we talk about the real world. So really what you have right here, think about this. You have right here in 28% of the time, he's not let out of class late. But then there's the scenario where this happens, where he's let out of class late and he misses the train. So what percent of the time would he be let out of class late and miss the train? So what percent of the time would he be let out of class late and miss the train? And we can see the mathematics right here. If he's let out of class late and misses the train, then it would be this right here for mathematics. So we just need to solve this. And we can see 0.72 times 0.25. And that's it right there. Now I'm going to do the next one in my head. I'll show you how, and I'll show you why. Because now we have the probability he's let out of class late. Oh my gosh. And the probability he does not miss the train. So the probability he does not miss the train. And this one right here should be, if we have right there 18, so it should be 54, I think. And I'll explain why it's 54 in a second. It should be this. The mathematics for this is going to be 0.72 times 0.75. And so when we solve this, 0.72 times 0.75, what do we get? We get 54. Now, how did I know this was 54? How did I know that that was 54 before I even did it? I could probably do 75% of 72 if I wanted, because 36 is a half and 18, so 70. I could have done it that way too. I could have done the math in my head, but I did it a different way. What we have right here, oh, the 75 is the probability he does not miss the train. Because either he misses the train, great question right there, Wilson. The probability he misses the train or the probability he does not miss the train. So he either misses the train or he does not miss the train. So there's three scenarios right here. The scenario one, he's not let out of class late, so he'll catch his train either way. Like there's no additional thing we'll solve right there. He's not let out of class late, so you could say he just catches the train. And then the probability he's let out of class late and misses his train, the probability he's let out of class late and he does not miss his train. So these are the three scenarios. And what do these three scenarios add up to when you look at all the probabilities? When you say either this could happen, this could happen, or this could happen, or this could happen. If we say or this could happen, or this could happen. So when we say this could happen, or this could happen, or this could happen, what do all these probabilities add up to? Because they're all disjoint. So every one of these is disjoint, and the probability would add up to what? The probability of all of these adds up to 1. Because 100%, yep, adds up to 100% because this is everything that could occur. He's either let out of class not late, he's let out of class late and he misses his train, or he's let out of class late and he does not miss his train. So this is every single scenario, and thus this is the sample space. Be very careful with the words sample frame versus sample space. The sample frame is, which is previous chapter, chapter 10, is every person or thing we could sample. The sample frame, I just said sample frame again. The sample space is every possibility of outcomes. So the sample space is used in probabilities. The sample frame is used in sampling. It's a similar concept, like everything we could observe when we have probabilities is the sample space. The sample frame is every person we could sample from. So it's kind of your frame or your space you're taking from. Slightly different words, but just put on note cards sample frame versus sample space. Sample frame is chapter 10. It's every person or thing we could sample from. And sample space is used in chapter 12 for every probability or every event that could occur. So it's every possible event that could occur. So hopefully, does this make sense right here? The answer to this question is going to be 18%, because I think it says the probability he's late and he misses his train. What is the probability that he gets out of class late and misses his train? Let's hope we did all our mathematics correctly. Check our answer, and we got it right. Let's go back to that first question now. And the first question right here is talking about sample spaces also. The sample space, once again, is everything that could occur. So it's every possibility that we have. And think about this. You have 2 coins, just 2 coins. And you flip the 2 coins, and what do you get? What did you get when you flipped your 2 coins? I love doing this example this way by going over here. And let's see what people in the chat have when they flip their coins. Let's go to sample. And let's do this. Let's go coin. And let's put a coin right here with heads, tails, and let's sample the coin. You know, and we need to sample 1 observation from it. There we go, it's heads. So I can flip 2 coins now. If I go to replace equals true, and now we can watch 2 coins being flipped right here just like this. You can just flip 2 coins, flip 2 coins, flip 2 coins, flip 2 coins. Now I'm gonna do something, I'm gonna make this 474 related really quickly right here, because I actually wanna see something real quick, and I wanna show you it. I guess what we could do, watch this. If you want to know the amount of times you get 1 heads, 0 heads, 1 heads, or 2 heads, which kind of relates to this question, I'll draw it out here for 201. We can do the following. Let's say heads. And let's go here. And let's run this right here. Sample this. And then let's do coin. And then let's do equals heads. So this will tell us how many of them are heads, or it'll say trues and falses. And then we can go to sum. And then we can store this into here. And we've now created a simulation where we can flip a coin. We now create a simulation where we can flip a coin. Let's do it 10,000 times. So this is a coin simulator, 10,000 flips. And let's make a histogram of how many heads we have. And there it is. Oh, I hate the way that looks. I hate the way, let me go to bins or breaks. It is in this. 5. That's better. I hate the bounce right there. Oh, you know what I could do? Much easier. Bar plot. That'll work better. It is quantitative, but really? Ooh, oh gosh. Horrible. Let's go back to the other graphics. That's the best we're going to do right now. Okay. So I don't really like the way this looks, but still fine. But what do you notice? You get 50% of the time 1 coin flip that's heads, 25% of the time 2 coin flips, another 25% 0% of the time. It's going to be easier to view this actually if we go to table. There you go. And let's do divide by There we go. And if we did re-simulate this, we might get closer, but as you increase the simulations, you get better and better probabilities, closer to the actual amount. So there's 100,000 simulations, and so then it's even closer. So this is a review of simulations right here. I'm increasing the number of trials to make a more accurate simulation, and we can observe, oh, I put one too many zeros. Sorry about that, because it should be 25%. So we have a simulation right here telling us the percent of time we get 0 heads, 1 heads, or 2 heads when we flip a 50-50 coin. And so what does this look like when we talk about it? Well, what we've done right here is we're talking about the sample space of the following. The sample space is heads, heads, tails, heads, heads, tails, and tails, tails. Notice how there's 1 heads here, 1 heads here, 2 heads here, and 0 heads here. We kind of went about a really long way of solving this, because you can kind of tell from the probabilities right here that there are 2 times you get this, 1 time this, 1 times this. So if the question asked how many heads you get when you flip a coin, you would not have an even probability for 1 heads, 2 heads, or 0 heads. But the question asks about this sample space right here, which this sample space, everything in here has an even probability of occurring. So, hey, what's up, Ahood? We just did a simulation real quick. I was like doing a little 32474, but we wrote a simulation to flip a coin 100,000 times. There's a coin flip 100,000 times. Did I make the numbers off? No, the numbers are correct. It's hard to see zeros. Feel free to ask some questions if you have them. Let me know. And so these are equally likely, because it's just asking about the heads, 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 tails, tails, heads, and tails, tails. Those are equally likely. Now, this one confuses people. Which of the following is the sample space of the number of girls in a family when a family has 3 children? What's interesting is we could do this in simulation also, because we can go right here and we could sample from this boy, girl. And so this is how we can answer these questions with code. And we've already written our simulation. So we've already written our simulation right here. And let's look at, because they're going to have 3 children. We can look at the number of girls, and we can do 100,000 trials. And I think I'll do it. There we go. Oh, shouldn't I have 3 girls? Sample 3. What happened? Oh, I'm still doing the heads. There we go. There we go. So if you think about this, the way it looks, it's actually kind of even or kind of symmetric. So this is the probability of having 0 girls if you have 3 kids, probability of having 1 girl, 2 girls, and 3 girls. And when you look at these probabilities, I'll do this to make them easier to look at. Interestingly enough, they are kind of near the middle. If you think about if you have boys and girls, just boys and girls, and there's a 50-50 chance, then what would you have right here? You'd have a more likely that you'd have towards the middle of even boys and even girls. We could even do this simulation where you have 8 kids and see what happens. So now this is a simulation where you have 8 kids, and the more likely scenario is that you would have around 4 girls. Let's round this to 1 digit. This is why I love coding. If you're wondering, it's just so easy to make it look nice and neat. And we can see here that the most likely scenario if you have 8 children is that you would have 4 girls. We can bring it right back to doing with 3 children. And you can see the most likely scenarios are that you would have 1 or 2. And this is a simulation. So if you notice the numbers are not exact, that's why you're like, well, why is 2 different than 1? It's because we're simulating it. What is the best way to say for the exam? We'll go over notes and how to prepare the exam. I feel like we've covered so much information. Definitely, when you go through the notes, look at each box in the notes that says something big, and make sure you have that, and the Kahoots. And I'm definitely, I need to go back. I need to take from the Kahoots. So the Kahoots are huge. And Wilson, feel free to ask any questions. I know hopefully I'm trying to make this also 320 related. But right here, you can see that the scenarios of 0 kids, 0 girls, 1 girls, 2 girls, 3 girls are not equally likely. Because think about it, if you have anywhere between 0 to 3 girls, well, then the more likely scenario is that you'd have closer to 1 or 2. 3 would mean you have all girls when you have 3 kids. 0 means you would have no girls when you have 3 kids. They are not all equally likely, because it's more likely you'd have 1 or 2 girls. It's less likely you'd have 3 or 0 girls. And we showed that via the simulation right here. So we're doing a little bit of randomness right here. We're showing that simulations can simulate real world events, and we're just doing the randomness part of it. What is the sample space for flipping a coin until you get 3 consecutive tails? So this one's a little bit trickier to simulate. How I like the simulation on it, but we want to go here and we want to go to okay, we want to flip a coin. So we want to bring our coin back. Oh, we called it coin. So we want to bring our coin back. We want to go to heads and we want to go to tails. So there's our coin back right there. And we want to go to while sample of coin 1. No, let's do this. While flips equals is it till we get a heads? Let me read it again. This one's hard to simulate. What is the probability of flipping a coin until you get a heads or 3 consecutive tails? So while heads while flips equals heads, the sum of it, I don't want to lose people because this is getting really complicated. Well, the sum of the flips equals heads equals 0. So while there's no heads and length flips is less than 4. So this will continue flipping the coin. Wow, that's crazy to write right there. Bunch of conditions right there. Oh no, let me turn on MuBot. I might not simulate this one because this one is crazy to simulate. Someone's gonna be like, can you not simulate it? But think about this right here real quick. I think the easiest question, so MuBot is awakening. MuBot is awakening now. So this one right here, if you look at the conditions I just wrote, we're gonna flip a coin and we're gonna keep flipping if we have no heads. So if you look at this right here, flip a coin until you get heads or 3 consecutive tails. So if you flip the coin first, and MuBot's back on now, Nicholas, thanks for reminding me. So now MuBot should do it. Yep, MuBot's there. So if you flip the coin, then what is something that could happen when you flip the coin? Who can flip the coin right now? Just flip the coin, and what happens? How do you do this question without coding? Yeah, that's a good question. Let's do it without coding. What happens when you flip the coin? Flip the coin for me, Wilson. Go ahead and flip the coin and tell me what happens. What did you get? Flip a coin. Boop. What'd you get? Heads. So what would you do now, Wilson? If you flipped the coin and got heads, what does it say to do? Flipping a coin until you get heads or 3 consecutive tails. What would you do? You're going to flip it until you get heads or 3 consecutive tails. So what would you do? You would stop. So now notice heads is one of the options. So you just eliminated this one and you just eliminated this one. Does that make sense? You just eliminated those 2 options because you're saying, okay, heads is something that could occur. Now, what if you had gotten tails? What would you do? If you had gotten tails, what would you do if you had gotten tails when you flipped the coin? If you had gotten tails, what would you do if you flipped the coin? If you'd gotten tails, what would you do? Keep going. What if you get tails again? If you get tails, then tails. What would you do then? If you got tails, then tails. What would you do? Would you stop? You would keep going again, wouldn't you? And so now you have tails, and now you could get a heads or you could get a tails. So do you see which answer it is on here? Do you see which answer it is that we would have where we're going to flip and we're going to get a heads? If we ever get a heads, we stop, but we'll stop at 3 consecutive tails also. If we get 3 consecutive tails, we will stop. But if we get heads, we will also stop. Which answer looks to be correct? Which answer looks to be correct on here? Because we'll stop if we get a heads. Anytime we get heads, we stop. But we'll keep flipping if we have until we get 3 consecutive tails. Like that's another stopping point too for the simulation. So which answer looks to be good here? I don't know. I'm just kidding. I know. A, yeah, exactly right. Nice job, Wilson. Exactly right. It's A. Because you'll stop here because you have 3 consecutive tails. Anytime you would get a heads, you would stop. So these are all possible stopping scenarios. Because once you get a heads, you stop. Now, what is the most likely thing to occur? Let's write down these real quick. We don't need to simulate it because we can just kind of theoretically figure it out using the laws of probability. We have here heads. We have here tails, heads, tails, heads, tails. What is the most likely thing to occur when you flip the coin? What is the most likely thing to occur? Out of all these scenarios, what is the most likely scenario? What is the most likely scenario out of all these? Heads or tails? And which of these? Scenario 1, hey, what's up, Aaron? So good to see you. So good to see you. Oh, you're talking about the hair. That's what you're talking about. You're talking about just the crazy hair. It's just getting crazy. So this one, think about this. We have this. You just flip a heads. You flip tails heads. You flip tails tails heads. You flip tails. So good to see you, Aaron. I hope everything's going well by you. And so with this, what is the probability of just flipping heads when you flip the coin? You need to come back on Halloween, Aaron. There's going to be a little chaos here. Little good chaos from the guy with green hair. So 50%. What's the probability of the second scenario? What's the probability of the second scenario here? Because now it's tails and then heads. So the key word is tails and then heads. And each coin flip would be independent of each other. So it's tails and then heads. So you can, if you look right here, we have the rules of probability. So it's tails and then heads. So with tails and then heads, what would be the probability of tails and then heads? So you see when I'm saying and the coins don't care about each other, we can do the multiple. Yep, 25%. So then what's the probability of the next one? Because then it's tails and then heads. I really hope everything. Yeah, it's crazy. Oh, I miss you guys too. Well, once I need to, we'll have a big coming back to Knoxville party or something. When, well, one, we're going to come back to Knoxville. And then two, when I come to visit to Knoxville, it'll be really great. We should do like a stock and barrel burger night if we can go out in the public world. I know we should do like Brian's telling all the students, like, come out to Stock and Barrel. Maybe we'll just like all hang out in Market Square or something. We'll just be like, Stock and Barrel burger night. We'll tell Stock and Barrel, try to get as many people to go as we can and be like, hey, just go to Stock and Barrel, grab a burger. Maybe, we'll just try to do something really fun, really nice. I wonder if I could like give them $100 and say the first 20 students get half price burgers. Rent cookout. Can I rent cookout? See, that'd be easier. You're right. The Market Square is not that far to walk. If you live on campus, I promise you Market Square is not that far to walk. I walk it all the time. Like it's maybe a 10-minute walk from campus, 15 at most. It's like if you're at the Hill, you're really close to Market Square. So I mean, University Center is pretty close to the Hill too. Our student union is now called. Oh, nice job, Dan. Excellent work. Great work. Wow, excellent. I'm so glad to hear that. We only did a few questions, but this basically has it. Really proud of you, man. I like hearing hundreds. I like hearing it. So you see, these are not all equally likely. 1 second. I'm going to see who it is at the door. I think it was just a package, and then my phone started ringing with a spam risk. So many things. This is what you get when you teach from home. What have we done? What have we done to the world? What have we done? What is the sample space of 2 dice? You roll 2 dice, and you're going to take the larger number. So we're going to roll 2 dice, and we're going to take the larger number. So just imagine you have 2 dice, and drop the larger number. I want to simulate this one. So Dan, Wilson, are you still here? I might simulate this one. If you think about a dice will be, and this is very easy to simulate, I think. So we're going to sample 2 dice right here. Does this make sense? So this is just a dice roll. So does this make sense when I run this right here? We're just going to sample numbers 1 through 6. And you see, we could get 3, 3. Does that make sense? So when you think about this, to simulate this, and so Aaron, this is a review of 4 loops right here. To simulate this, we're just going to go here, and let's take the max from the dice, minus 3 dice. Oh, let's do 3 dice. You ready? Here's 3 dice. This is why I love coding. Hopefully someone's like, I like coding too, or people might be like, oh, there we go. There's 3 dice. And now what are we going to take? We're going to take the max from these dice. So do you see how I now have the max? And then we're just going to store this max into largest dice. So we're going to store this, and we're going to store it into the first observation of largest dice. Largest dice does not exist. And there we go. Now we can store it here, and this is the largest dice. Now we could do another simulation where we simulate it again and store into the second of largest dice. And you see we're just taking the largest dice. But does this make sense right here, Wilson, that we're going to take 3 dice, you're going to shake up the 3 dice, and when you do this, you get that you got 3, 2, 1. Now what would we store into the third position of largest dice? So I dropped 3 dice, and they were 3, 2, 1. Hey Dan, have a great day. What is the largest dice I would record there? 3, you're right. And that's what my code is doing, is it's taking that. Now I'm going to simulate again. And what dice will I store here? 2, 5, 1. This is just the position I'm changing. So I have 3 dice I dropped. It's 2, 5, 1. So what dice will be stored into the largest position there? Or the largest dice? What dice would be stored there? 5. And so you notice here the last number stored is 5. So what I'm doing with this code right here is this code is just going to run a whole bunch of times. That's what a for loop does. The for loop is going to run this 100,000 times. So I'm going to do that same code we just witnessed right there 100,000 times. And I just did it 100,000 times. Now I'm going to look at the results. And here's the results. What number was most likely to occur and why? So this is with 3 dice. What number was most likely to occur and why? With 100,000 rolls of dice, what number was most likely to occur and why? And then let's think about why when we drop 3 dice, this number would be the most likely one to record if we record the highest dice. Yeah, 6, because anytime we roll a 6, like if you roll a 6 and then a 1 and a 1, you'll record a 6. If you roll a 6 and then a 2 and a 3, you'll record a 6. If you roll a 2, 4, 6, you'll record a 6. Because anytime 6 is rolled, it's the largest number. So that would be, it's again, yeah, once we roll a 6, we're like, you could say you roll a 6, okay, then you're recording 6. It doesn't matter what the other 2 dices are. So the only way to record a 1 would be to roll what? If you're going to record the largest number each time, what is the only way we would record a 1? What is the only way to record a 1 if we're going to record the largest number each time? If we're going to record the largest number, what would we need to roll 1? There's only one scenario where we record 1. We'd have to roll. I think you know it. And that's why this is the sample space. 3 1s exactly. So do they sound equally likely? Because the only way to to get a 1 recorded is to roll 1 1 1, and then you record a 1. And then there's so many ways to record a 6. You could roll 1 2 6, 2 6 1, 2 3 6, 6 6 4, whatever you want, and you would record a 6. So are they equally likely? No. Now they changed the positions of no's and yeses, so watch out. I think that's the only one that's equally likely. I hate that they changed where the no's and yeses are. Whoo, got a little bit scared there because they changed where the no's and the yeses are. Watch out because that's no yes, that's yes no, that's no yes. I hate that they permutate those results sometimes, but just watch out because yes and no is not always in the same spot. That has tricked me before. Boom. Great job right there, Wilson. Love it. Which one are you working on next, Wilson? You name it, we'll work on it. Lots of good review there. I hope you had some fun with the simulation stuff. So which one are you working on next? Is it the homework? We can knock out the next homework one. Is it the spinning the wheel one? Feel free to say which one. Plastic arrow. Yeah, I think it's the plastic arrow on a wheel. Hey, what's up, Isaiah? So good to see you. Feel free to ask any questions you have. We're just working on some probability right now. We can hop into whatever topic you want. We're going to work on the plastic arrow question, but feel free to say, hey, Brian, I'm working on this problem, or can you explain this topic? And I'll be happy to go over any of the topics. Am I in the homework right now? Plastic arrow question. So there's a few rules for probability. The rules, I have homework and quiz up so you can pick. Oh yeah, no, that's fine. We'll do any of the questions you want. I jump around between questions if there's more people asking questions, but you're here, so we get to focus on your work. So it's like, hey, some people, I want people to know I'll help to tutor, I'll help to do those things. And I like having the videos up so other people can watch it. Because some of these videos get, like you might be watching it now, some of these videos get 200 views or so. That was Amazon delivering my chewy dips and 2 other items. I think it's granola bars. Everyone needs to know what my Amazon package was. So with this right here, a monthly Amazon pantry package. So we have a child spinning wheel right here, and it has colors on it. Now there's rules of probability. You're welcome, Wilson. The rules of probability are, well, the first rule outside the multiplication, addition, and complement rule are, 1, probabilities are all between 0 and 1. What? Yeah, exactly. It's pretty chill in here. That's usually, it's pretty chill. Some people like watching the VODs, the videos on demand, and then it's usually pretty chill in here. We go through slowly and we work the problems. So I'm glad we have this kind of supplement. Things were great. Sample space needs to add to 1. So these are the two rules that we'd be going over right here. Just 2 rules. And probabilities all have to be between 0 and 1. 0 means that it cannot occur ever. 1 means it always occurs. And the sample space needs to add to 1 means that if you have all the probabilities, that they would add up to 1. So we've seen this in scenarios already today, where we have a sample space here. All the probabilities are between 0 and 1. Meets both rules. We had the scenario, that's just counting observations. We had the sample space right here. All the probabilities are between 0 and 1, and they add up to 1. So we're meeting these 2 rules. And really good practice that we've been doing today on that. So those are the 2 rules. So let's look at the first wheel. The first wheel is 40% red, 10% yellow, 40% green, 10% blue. Does that wheel sound like it can exist? Yes or no? So just simply yes or no, does that wheel sound like it can exist? It's like a spin wheel someone has, 40% red, 10% yellow. It totally sounds like it exists. It is possible. And this is the good answer right here. Great job, Isaiah. Yep, you are totally right. 100 points for both of you right there. Because they add to 1 and all probabilities are between 0 and 1, which are the 2 rules we stated right here. So probabilities are between 0 and 1, and the sample space needs to add to 1. Both of these are listed right here, and this is the right answer. This means it's good. Now the next wheel is 40% red, 40% yellow, 110% green, and negative 190% blue. Now this does add up to 1, but think about what I'm saying right here. So is this possible, yes or no? Kind of the easiest thing to identify first. Is it possible? Is it possible? Could this wheel possibly exist? Exactly. There's probabilities outside of 0 and 1. At least one probability is not between this. So there's numbers that can't exist. How about this one? This one's 25% red, 25% yellow, 25% green, 25% blue. It's a very easy wheel to draw. So it's 25% all those colors. Let's go right here and just do a cross through it. And we'd have 25%. And really? Computer going to be weird today? 25%, 25%, and 25%. So 2 them being outside. Yeah, exactly. And so this wheel is very possible because every number is between 0 and 1. It's just a wheel that's 25%, 25%. Just try to think about it conceptually what this wheel would look like. It's just, like Assignment says, or, we have to press the buttons. It's just a wheel like this that's 1/4 each color. So that's what we're talking about here visually, is what would these wheels look like and could they possibly exist? So 1, we just drew this wheel. So yes, this wheel can exist and it meets the conditions that all probabilities are between 0 and 1 and they add up to 1. Now this wheel right here is 20% red, 60% yellow, 10% green, and 10% blue. Nice job, Isaiah. Excellent work. So can this wheel exist? It's like saying, okay, I'm going to give my money away. I'm going to give 20% of my money to you, 60% of my money to you, 10% of my money to you, and 40% of my money to you. Can this wheel exist? Can this? I think I know what you're saying, Wilson. What do you mean it's outside of 1? It cannot exist. What do you mean it's outside of 1? I think I know what you're saying. Like expand more on it's outside of 1. I know. Like, are you talking about the probabilities or the sum of the probabilities? Are you saying probabilities are outside of 0, 1, or are you saying the sum of the probabilities is greater than 1? Because I think I know what you're saying. I think you're saying the sum of the probabilities is greater than 1. Does that make sense right there? Do they have a sum probabilities less than 1? Oh. Yeah, it needs to add up to total probabilities greater than 1. Exactly. Boom. Got it. Awesome. And then this last one right here, this is a wheel. Explain to me theoretically what this wheel would look like. Explain to me theoretically what this wheel would look like. What theoretically would this wheel look like? Theoretically, what does this wheel look like? 100% red. Totally possible. So, yep. It's just a wheel that's red. It's just a red wheel. Totally possible. Awesome job, Isaiah and Wilson. Great work. We got another one right here. So suppose that 43% of families live in a country, own a tablet. Wait, 43% of countries own a tablet and 19% own an HD TV. I was like, wait, what? The addition rule might suggest, did they upgrade it to tablets in recent years? And the addition rule might suggest that 62% of families own either a tablet or an HD TV. Now, whenever you hear the word or, and I'll make sure we see this as review. If you see the word or, we're talking about the addition rule, and you should know the following things. You need to see if they are disjoint. Disjoint is the same thing as mutually exclusive. So disjoint is the same thing as mutually exclusive. That's not margin of error. Mutually exclusive means that two things do not overlap in their probability. Here is mutually inclusive. Here is mutually exclusive. So this is disjoint. This is not disjoint. So could there be people who own an HD TV and a tablet? Or is it that people who own HD TVs don't own tablets? Does it sound like this is disjoint or not disjoint, that people who own HD TVs can also own a tablet? So you would add living in the country and owning a laptop? You can't add them because I think it's like sometimes they have like owning a laptop and owning an HD TV, because in this question, the two things are not disjoint because there's an overlap, so you can't use the addition rule as is. There's a way to solve it. People probably know it's probability of A plus probability of B minus the union of the two, the overlap, because you had the overlap twice. But no worries, we won't put that on the test. There's ways to handle things that we don't talk about, but not that we don't talk about that here. There's just more advanced probability laws that we don't talk about because we don't teach a whole class on probability. We just teach a section on it. So does this make sense on why you can't just simply add them? Because if you add them, you'd have a problem because there's people who own both items, so you can't use the rule of addition where we're adding things that are not disjoint. Make sense? Or perfect. So that's the visualization. Some probabilities. If families own a tablet, no influence. This is talking about independence right here by saying influence. If family owns a tablet, the events are not disjoint. Yeah, so that's all I need to read. By them saying the events are not disjoint is the key to this question, because the rule for adding things together is disjoint. So that's a giveaway. I mean, they could try to trick us, but with right here, addition being the disjoint rule, mutually exclusive is another word for it. This is the key to the question. And remember, disjoint means if A happens, B cannot happen. Yeah. Which are you talking about the first one right here, Nick? Is it the very first one? We did it earlier if you want to rewind, but we can go back to it here in a moment. We'll finish off the homework and then we'll loop back and do it. Does that sound good to you, Nick? So we can go over the heads and the tails one if you want. And which one specifically? Because there's two of them, I think. So we can definitely do that, Nick. We got tons of time today. We got an hour and 15 minutes. Yeah. And tell me if you have questions. Tell me if you have questions on it. So tell me if you have questions. Then we'll keep putting more stuff in the video. And you got it, Nick. Thank you so much, Nick. Nick, 100 points right there. That's awesome. Appreciate it so much, Nick. So traffic checks on a certain section of highway suggest that 70% of drivers are speeding there. So since 7 times 7 equals 49, the multiplication rule might suggest that there's a 49% chance that two vehicles in a road are both speeding. What's wrong with this? So what do we need to assume if we're going to multiply things together? What would we assume if we multiply stuff together? To multiply two probabilities, the two probabilities must be what of each other? Here's a hint. I just want someone to say the answer. The hint is this. What must we assume if we're going to multiply two probabilities together? Well, that's the answer. What must we assume if we're going to multiply two probabilities together? To multiply two probabilities together, we must assume they're independent. So what does independent mean? It means if you know the answer or you know information about one, it does not give you information about the other. So let's say we got, it's 5 p.m. and it's like height of traffic and all the cars are just jammed up on the highway. How fast do you think these cars are going? Like if this car here is going 10 miles per hour because there's a traffic jam, how fast do you think this car is going behind it? You think that car is going about 80? You think it's speeding? That's how close the cars are away, and this is a realistic drawing. So this car right here in the red is going 10 miles per hour. Does that give you any information on the speed of the other cars on the highway? Would that give you information about the speed of the other cars on the highway? About 10 or less. I agree. Hopefully 10 or less. So you would say that this car right here, this car behind it, its speed is what of the cars ahead of it? Its speed would be what of the cars ahead of it? Or not independent. It would be dependent. The car behind it would be dependent of the other cars. So can we multiply them together? The answer is no. Because knowing the speed of cars on the highway would give you information about the speed of the other cars on the highway. And that's what independent means. Be very careful to know the difference between disjoint and independent. Actually, disjoint events are completely dependent because it's not to say independent means disjoint. It's just that disjoint events are dependent because if a disjoint event happens, another event that is disjoint to it cannot happen. So these are different concepts, different concepts. I feel this is one of the harder parts of this chapter is understanding what disjoint means, understanding what independent means. I'm happy to go over that. When test time rolls around, you'll hear me talking about it like 2 or 3 times. But understanding disjoint means if A happens, B cannot happen. So because it's dependent, you can't multiply exactly. It does not meet the independence rule. Since it is dependent, we cannot multiply exactly for this question. So to multiply together, we need to meet the rule of independence. So there are cases where they're not independent. Boom. Yeah. Since there are cases when they're not independent, that's the key right there. They are not independent. Now we get to some tougher questions. These are the tougher ones. First one's not so bad. Second one, a little trickier. So a consumer organization estimates that over a 1-year period, 16% of cars will need to be repaired once. The 5% will need to be repaired twice. 3% will need to be repaired 3 times. 16, 5, 3. Okay, let's write this down. So we want to write these down. Make sure we have some notes on it. Let's make some bigger text. Probably this one, Lightbulb one. Yeah, they truly are. They are tricky. Probability 1 is 16. Probability 2 is 5%. Probability 3 is 3%. So what are we missing? Oh, it's 3 plus. It's 3 plus. What are we missing from the sample space of possible events right here, or possible outcomes? So this is your car. What's the event we are missing or outcome we are missing? No repairs. Bingo. And so we could do the complement of the other items right here. Let's add them up. And the probability of repair is going to be an excellent work right there, Wilson. Great job. We'll have this quiz done, homework done. So it's 74% because this is the complement of getting a repair. And so the probability, we wrote it this way. There we go. And so this right here is 26%. Color changing pen. So that's 26%. No, it's 20. Something weird happened. There we go. Yep, that's right. There we go. I was looking at it, I was like, that's not right. You look at it and you say, no. There we go. So it's 24%. Always double check your math. Easy to make mistakes. I made a mistake on this problem last time I did it. So here we have all the different probabilities. Now let's go ahead and look at the problem and see what we have. So it says the probability that the car will need no repairs. Well, we just figured that out. 76%, right? Good to go. The probability that a car will require no more than 1 repair. No more than 1 repair. So you say, oh my gosh, if my car gets more than 1 repair, that'd be bad. Well, more than 1 repair would be the following. Here's more than 1 repair. Here's no more than 1 repair. More than 1 repair is 8%. So via the law of the complement, no more than 1 repair is 92%. You could add these together because either you get 0 repairs or 1 repair, and these are disjoint events because your car can't get 0 repairs, also get 1 repair. Because if you get 0 repairs, you get 0 repairs. If you get 1 repair, you get 1 repair. These are all disjoint occurrences. They do not occur together. So 92%, the probability of 0 or 1 repairs. And the word or there is key. When I say the probability of 0 or 1 repair, I'm using the addition rule right here to say the probability your car gets 0 or 1 repair. So we can just add together these probabilities right here to say the probability of 0 or 1. Or we could use the complement to say the probability your car does not get 2 or 3 plus repairs. So 2 ways to solve it there, one with the addition, one with the complement rule. And looking at the next one, the probability that a car will need some repairs, well, either your car needs no repairs or it needs some repairs. No repairs is 76%, some repairs is 24%, and that's got the easy one. Now this one's a little bit trickier, but don't worry, we got it. In this one, we're looking at different numbers, so 17, 7, and 1, 1771. And so let's go here. Let's delete off our 17, 7, and 1. So 17, 7, and 1. And I think that goes to that. That does. Okay, good. That puts the probability of some repair at 25%. I don't know if we'll use that one this one. I can't remember for the moment. There we go. So now we have the probability of all the different ones right here. All we did was take the numbers given to us and put them here for us to see with the probability of a 1 repair, 2 repair, or 3 plus repair. And then we did the probability of no repairs also. So we are good to go on all these numbers. Now the first question asks, you have 2 cars. And with 2 cars, what's the probability that your first car does not need repair and your second car does not need repair? What's probably your first car does not need repair and your second car does not need repair? Your first car does not need repair and your second car does not need repair. So we have to go back to the sheet and we have the probability that the first car needed no repairs. So let's go right here. Multiply exactly. Great job, Nick. We're going to multiply here. This is probability of no repair. So the probability of no repair, and this is the probability of repair, equals to 0. We're doing this percentages. 75%. So the first car did not need repairs, and the second car did not need repairs. 0.75 times 0.75 is 56.25. Wait, what? Oh my gosh. 0.75 times 0.75. This is what we do in our heads. There we... Wait, what is going on? Dividing. Oh my gosh. There we go. That's why you check the math in your head. It made no sense that would be 1. I just don't know how to press buttons on computers. So there we go. The next one, the probability that both cars will need repair. So now we have the first car needs repairs and the second car needs repairs. So we're using the rule of multiplication right here, as Nick pointed out, because the first car needs repairs and the second car. Now we have to assume that they're independent, which you might say, well, wouldn't, if a car needs repairs, maybe influence the other car to need repairs because you're going to drive it more. I do agree there might be small issues with the theoretical working of this problem, but it doesn't give the option to say, theoretically, we can't do this. So the first car needs repairs and the second car needs repairs. Who can solve for the probability the first car needs repairs and the second car needs repairs? This is just how many repairs a car gets. This is the probability the car needs repairs, does not need repairs. This is the probability the car does need repairs. So what would be the probability, just show me the mathematics, that the first needs repairs and the second needs repairs. The first car needs some repairs, and then the second car also needs some repairs. The first car needed some repairs, and the second car needed repairs. I'm going to draw something out here real quick while you're doing that. So repair, 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 no repair. And so just think the first car, what's the probability your first car will need repairs? Well, so what is just the probability the first car will need some sort of repair? So these are not the cars right here. So you can actually, I know this sounds crazy, you can actually kind of ignore this now. Because that, no, I don't think that's the answer. I think I know the answer in my head. So this is the probability of some repair. Exactly. This is the probability of some repair. This is the probability of no repair. Does that make sense? Because all this is telling us is how many times a singular car got repaired. Your first car could get repaired 0 times, or 1, 2, 3 times. Your second car could get repaired 0 times or 1, 2, 3 times. So either your first car needs no repairs or your first car needs some repairs. Either your second car needs no repairs or your second car needs some repairs. So what's the probability your first car needs no repairs is this. And exactly, Nick. Nick, you're exactly right. It is 25.25 squared, which should be 1/16, which should be 6.25. So it should be 0.25 times 0.25. And I've listed it out over here, and there it is, 66.25. So we can put this right here as, and this is repair, 0.0625. And then the first one over here, no repair, was 0.5625. So the probability of no repair was 75 times 75. The probability of repair was 25 times 25. So 0.0625. And there's that. The probability that at least one car will need repairs. Now this is where what I've written, oh my gosh, it's a busy day. What I wrote over here is a very helpful thing for this problem. Because what I've listed here is the what. What I am highlighting for you is the what of what could occur. What I'm highlighting here is the what. I've just highlighted that either both your cars need repairs, first car needs repairs, second car does not need repairs, first car does not need repairs, second car needs repairs, first car does not need repairs, second car does not need repairs. All the outcomes, the sample space. So tell me, if I call this right here X, could you write an equation right now? So if this is an equation where all of these things right here have a probability of X if we add them up, could you figure out an equation right here? Because what I've shown you is your car getting some repairs. One of your cars getting a repair. So what would this be if we wrote this as equation? Wouldn't it be 1 equals X plus 0.5625? Does that make sense when I say an equation for this? Because this is going to be, because what I've done right here is I've said, this is everything. Yeah, hopefully, yeah, it's making sense now, I think. So this is everything that could occur. So what can we do? We can just, how do we find the answer to what X is? How do we solve for X? How do we find out the remaining probabilities? Yeah, it makes it easier to see. Yeah, that's what I'm hoping to show, like graphically and visually right here. If you follow along, you're like, oh, okay, that's it. So we're just saying either neither of my cars need repairs or at least one of my cars need repairs. So when you look at this, we're not interested in this one because this is none of your cars need repairs. We're interested in at least one of your cars need repairs. So either neither of your cars need repairs or at least one of your cars need repairs. I think show me the mathematics. Use this right here because this is the answer to it. If you solve for X with that, then you'll have the answer. So as long as we just take and we do what? Because we don't want to see that none of your cars need repairs, and that's kind of the answer there, because it's everything but none of your cars need repairs. So what will we do? Yeah, exactly. Nice job, Isaiah, right there. That's exactly it. And that'd be 43.75. I think 43.75. Phone, stop going crazy. Chill out. 0.4375. There we go. And if you're wondering, we just took 0.5625 and we did 1 minus it. Oh my gosh. 1 minus, really? 1 minus 0.05625. So, what? 1 minus 0.5625. Okay, good. So that is the answer right there, and that's how we do it. Now this one seems really tricky, but it's going to use the same format. We have right here, you purchase a 5-pack of new light bulbs that were recalled because 11% of the light bulbs did not work. What is the probability that at least one of these light bulbs is defective? So let's think about this visually right here. Let's go through it visually and take a look at the possible scenarios. When we think about this, we have right here that one of our light bulbs could be broken. So one of our light bulbs, oh my gosh, 1, 2, 3, 4, 5, 6, or 0. So close. So what you have right there, let's take a look at that. So the probability of a defective light bulb, so probability defective was 11%. So the probability of a defective light bulb is 11%. The probability of a good light bulb is 89%. So what are you worried about? You're saying in this problem, I think it's at least one is defective. What's the probability that at least one of your light bulbs is defective? So think about this. When you open the pack of light bulbs, and it's a pack of 6. This is how I got this wrong last time. 5-pack. I did this too. So I made the mistake last time on it. So you open a 5-pack of light bulbs. Every time I buy them, they come in a 4-pack. I don't know this 5-pack of light bulbs thing. So when you open a 5-pack of light bulbs, there's either 0 defective, 1 defective, 2 defective, 3 defective, 4 defective, or 5 defective. Does that make sense? A certain amount of your light bulbs will be defective in here. Now, what does 0.55 to the 5th power solve for? What would this solve for right here? 0.11 to the 5th power would solve to what? Not mathematically, but what does it mean? And here's what it would sound like if I talk about it. I would say this times this times this times this times this. So what would this be? This would be the first was defective, all are defective, exactly. The probability of all the light bulbs being defective, which is actually the probability of this right here. We just solved for that. So we just solved that every single light bulb is defective. So wait a minute, what would this one be? What would be the mathematics on this one down here? So if we were to solve for the mathematics of the other one, wouldn't it be this right here? Let me copy paste, that'll work. Wouldn't it be this all the way on the other end? Because wouldn't this one be the probability that none of them are defective? That the first was good, and the second was good, and the third was good, and the fourth was good, and the fifth was good? Not we're saying fifth right here, but you open a 5 thing of light bulbs, and all the light bulbs are good. Light bulb moment. There you go. Awesome. Yes, this is, and so visually, I hope this helps, because this is the way I see it in my head. But wait a minute. I think we just found the answer almost. Because we don't want to see, I like the pun, 100 points for the pun right there. We don't want to see that all the light bulbs are good. We don't want to see this. This is what we are not interested in. So let's do this. This is what we're not interested in. We're interested in this over here. We're interested in at least one of the light bulbs are defective. Does that make sense? We're not interested in every light bulb being good. We're interested in at least one is bad. So we know the probability of 0 is this. How can we figure out at least one is bad? Because either they're all good or at least one is bad. Now, what am I saying when I say either they're all good or at least one is bad? Because you could write that this way. You could say 100% of the time, all good or at least one bad. So writing it out this way, the all good is the red, which we don't care about. We don't care about the red one right here. And the at least one bad is what we want to solve for. So either all the light bulbs are good, which this is the scenario we're interested in, or at least one is bad. Wait, or. If I'm saying or right here, isn't or our word that we use? Isn't or the word we use for the addition rule? Isn't or how we solve an addition rule thing? So can't I just, because they're disjoint? Yep, we're adding them together. You're right. Just, yeah, you could add these together. Wait a minute, but don't we know the probability of all good? Isn't all good right here? Isn't this probability right here just 0.89 or 89 raised to the 5th power? Wait a minute. Wait, did we just solve this? What? Well, we just solved it. We now have the answer for at least one bad, because we just did a very similar problem to what we did last time. Sure, I won't erase it. There we go. All we're going to do is just take this right here and bring it over here. And there it is. At least one bad. That's the answer. There we go. We've done it. Does that make more sense when we view it this way? That either they're all good or at least one is bad. So it's everything but. That's why I like to say this. I say everything but all the light bulbs are good. So when I talk about this as words, I say everything but all the light bulbs are good. And that'll be the answer. So then just be careful how you solve it. 0.89, 2, 3, 4, 5. There we go. 1 minus that. Copy the number. Bring it back over to the document. And 3. There we go. Got it. Good. Good stuff. What other question? Nick, do you want me to go back and do the other one? Any questions people have? If you have questions, I have answers. Today is a harder lecture in 201 today. If you have questions, feel free to ask. We can go back and do the first one. Wait, 60%? I think, oh no. We might need to go back. We did earlier. Do you say you want me to do it? I don't know if that yes is for the I said this 60% is gonna kill me. It's already in the video, so I can just do it real quick. Are you ready? Here's the sample space right here. Are they all equally likely? It's just gonna kill me if it says 6%. Are they all equally likely? Yes. And then what's the sample space of kids you can have? Are they all equally likely? No, because you can have, you're closer to have 1 or 2 of the boys or girls. Sample space of flipping until you get. Are they all equally likely? No, we did the work on this earlier because heads is the most likely at 50%. And then flipping, rolling dice 3 times, 1 through 6 are the numbers. Are they all equally likely? We're recording the smallest number. Doesn't matter smallest or largest, they're not all equally likely. Thank you so much. You're welcome, Isaiah, of course. Easy 100 on the homework. Awesome. See you later. Wacky Wednesdays, you bet. Where you at, Crash? You come back. Wacky Wednesdays with rainbows right here. Can you do the song on the quiz? Yeah, of course. Let's do that. We get 100 on the homework now. That's what we want to see. Even I like to see that 100. Just makes you feel good to see a 100. Let's do the song 1 on the quiz. That's the worst song ever. Here we go. Okay. The song 1 is it question 7? We did this one earlier. Short one. Okay, right here we have your favorite songs contained. So we have our favorite songs, and we have 7 rock songs, 10 rap songs, and 3 country songs. So we can put down here the probabilities. And so to do the probabilities, 7, 10, 3. Okay, let's do it. Okay. So the probability, what were the names? Probability of country. Oh my gosh. Probability of rap. Oh my gosh. Probability of, what was the last one? 7, 10, 3 is the order. Rock, rap, country. 7, 10, 3. Okay. So rock, rap, country. And then country. And so it's 7 out of 20. And 10 out of 20. And 3 out of 20. You have a very small playlist. So here's the probabilities, and we can rewrite these to be what they are mathematically. 35%, 50%, and 15%. So in this one right here, we have these probabilities. Now, if you put a song on, apparently it can be only one of these genres. We're saying that they're disjoint. So, I don't know, no country rap, no rap rock, no things like that. So what is the probability that a randomly select song is a rap song? Well, we should be able to minimize this. So a randomly selected song being a rap song. I went to go to the wrong page. I did. A rap song is going to be 50% because half your songs are rap songs. What's the probability that it's not country? Well, not country is the complement of country, and country was our 15%. So that's complement right there. Yay! So this is just the complement right here. So it's saying either it's country or it's not country, and the probability of country is 15%. So the probability of not country is 85%. So, and that's just a practicing of the complement rule. So really good question right there. Good practice. You purchased the 5-pack of light bulbs, 14%, 86, at least 1 defective. If you know the trick, you should know why we work this problem this way though. So don't just memorize how to solve this one problem, understand the theory behind it, and then any problem we give you related to this would be very easy. So theoretically, understanding how I did that, if you're wondering how did I do that so quickly, we just worked this problem over here and we talked about the theory behind it. So understanding the theory and being able to write it out, being able to draw it out, and understanding what you're solving for and what my drawing here means is very important. So the better you understand the problem, the easier they are to solve. Just like this one right here, if you buy a 6-pack of soda, what's the probability you win something? So it'd be everything but they're all losers. So you're buying a 6-pack of soda, everything but they're all losers. 2, 3, 4, 5, 6. 1 minus. There's the answer. And we've solved it. So, and I think that goes to an 8. Now, I'm going to slow down this problem and redo it right here because I was able to solve it in seconds because I know what it's asking and I know how to talk about it. So let's talk about what I did when I thought through this problem. It said the probability you win something from a soda cap is 19%. So the probability of winning, let's go here to probability of winning is 19%. Thus, the probability of not winning, which is losing, because either you win or you don't win, at least when it comes to a soda cap. You either win or you don't win, and so we can just call it losing right here. Most people would define not winning something as losing if it's just you pull off a soda cap and you see if you win. So you buy a 6-pack of this soda, drink all of it. When I was a kid, we used to go to McDonald's and buy sodas from McDonald's because they had the Monopoly pieces. And we'd get like $5 and we'd go and buy like 4 sodas from McDonald's and drink. My gosh, that was such a horrible idea. I drink like 4 large McDonald's sodas. Someone's like, why did you have to drink it? And I was like, I don't know. I think we were like, oh, if you drink it. Nowadays, I'd be like, what was I doing to myself? Horrible ideas. So anyways, this is what could occur. You could win 0 times. Oh yeah, there's the whole like the guy who cheated it, and wasn't it related to the mob? Wasn't there like mob stuff? I actually won $50 from McDonald's Monopoly. It was the coolest thing ever. Like the piece was all like rainbow. It said like instant winner $50, and I think it was only 50. I'll have to check with my mom again. I'm pretty sure it was 50. May have been 100. But yeah, I definitely won instant ticket with my friend Chris Lankenpoop, and that's his name. Oh shit, I didn't say his name. But anyways, and he was in the car with me and he's like, I could have won. That could be mine. You owe me half. And then my mom said, well, I paid. And so Chris didn't make me give him half the money. But yeah, I remember he was just like, that could have been mine. And if it had been his, I'm sure my mom would have been like, congratulations. And I'd be like, but, and she'd be like, it's his. He pulled it off. You know, so, but yeah, so that was pretty cool winning that. I think we were going to like school or something, or we'd gotten home from school. Can't remember what it was, but I remember pulling it off and being like, whoa, I won $50. So it was really fun right there. Kind of crazy experience. Remember it. Oh, and I remember when I got the check and my mom was like, okay, how much of this are you going to save? How much of this are you going to do this with? And good financial planning. One last aside I want to say is always, I know it's, yeah, you don't want to be bogged down in all this thinking stuff. Thinking's too hard sometimes, but try to make smart decisions and smart life plans for money because it can go out of control really easily. In college, Brian, life lessons with Brian. Where's this? There you go. Life lessons with Brian. In college, I definitely rung up a credit card or two, and luckily I only rung them up to like the tune of like 3,000 or 4,000, and 3,000 or 4,000 is not pennies. It's not little bits, but 3,000 or 4,000 is easier. Yeah, actually, I've had it for a while and I just haven't used it in a while. It's easier to get yourself $3,000 or $4,000 out of the hole than it is 10, 15, 20, 100,000. And I think my biggest advice for people is to make a budget and stick to it. It sounds crazy, and somebody like, I don't want to stick to a budget. I just want to, just blah 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 blah. But if you plan out how much money you have coming in and how much money you're spending, then you can accurately look at where you'll be at. And you always have to plan for, yeah, exactly, smart financing. Yeah, it's hard though. It really is hard to stick to it. Just try to think about the little changes you can make. One big change I made, and I don't get coffee anywhere now, or I don't even make my own coffee anymore. Long stories on those. But I decided I was going to only go to Starbucks as like a big treat. And so I'd only go to Starbucks maybe once a month. And going to Starbucks, even just to get a tall coffee or something, even in the refillable cup, which is awesome. Yeah, exactly. Yeah, oh, man, I'm so sorry. It's got to be hard doing this during the global pandemic. Yeah, making your own coffee is key because you can make your own coffee for a pot for like $1. And so you could get 3-4 cups of coffee for $1, probably even less than $1, because a bag of coffee is like a big bag of coffee you can get for like $8-10, like a pound of coffee. And then if you grind it, and if you grind your own coffee, it's pretty good. So, but don't just go out and be like, I'm going to buy a grinder, I'm going to buy a French press, I'm going to buy this and that, and then you never use it. That's what I've done multiple times. I'm one to speak. But start small and buy something, and then make sure you use it for a month. So if you buy something like a coffee maker, don't go and buy, don't go and buy 10 things. Just buy one thing and say, okay, if I use this, I can then, next month I can buy something else that I'm going to use to keep my finances in line. So don't, this is me talking to past self. Don't go buy 5 things and say, I'm going to save money these 5 ways. And then you never use any of them, exactly. So if you make your own coffee, it's way cheaper. And if you get pretty good at making your own coffee, you can make some pretty good of your own coffee. Okay, it doesn't compete with pumpkin spice latte, I'll admit it. That thing is insanely good. But you can, that's why you treat yourself to a pumpkin spice latte. Then it's really special. And when you get it, you're like, oh man, pumpkin spice latte. You're not like, okay, I'm going to wake up, get my pumpkin spice. Of course, now I miss it. Okay, how did I solve this problem? That was our little bit of fun right there. So what you're looking at right here, I need to put like, do this. Problem starts here. Okay, this is for future Brian. When he puts the timestamp in. So I can see the timestamp and be like, problem starts here. Okay. So in this problem, what are we doing? Not that we have a discussion before this problem. In this problem, we are talking about bottle caps when you twist them off, like McDonald's Monopoly, and you see if you won or lost on it. Now, either you win or you lose. And we're not saying what you win or what you did not win, but we're just saying the probability of winning is 19%. The probability of losing is 81%, because either you win or you do not win. So you're going to buy a 6-pack of soda. Now, each of these represent outcomes that could occur. Nice job, Total Pog right there. Amazing work. We have right here that you could win 0 times on the 6 sodas you buy. You could win 1 time, you could win 2 times, you could win 3 times, you could win 4 times, 5 times, or 6 times. So this is the amount of times you win, not you won on the 6th time. It's that you won on every single bottle cap you twisted off. So think about this. Just if you were to win on the first bottle cap, what's the probability of just winning on the first bottle cap? What's the probability of winning on just the first bottle cap? Someone in the chat tell me. These are my big questions times. What's the probability of winning on just the first bottle cap? You take the first bottle cap, what's the probability you win? Look at that. What's the first bottle cap, what's the probability you win? First bottle cap, what's the probability you win? So make sure to be looking up at the notation we have for it. On the first bottle cap, the probability you would win would be 19%. The probability you win on the first one, oh, no worries, no worries. Great work. It'd be 19. Don't worry, Nick. Don't worry, Nick. It'd be 19%. 19% is the probability you win on the first bottle cap. And then we twist off the next bottle cap. Now, what is something we can assume about all these bottle caps? Each one you're twisting off is what of the previous one. When I say and then, what do we have to assume about each bottle cap? Or each top. Each top we twist off is going to be what of the previous one if I say and. If I say and, we have to assume, and I keep switching between what we're using, so I go back here and it's a different one. Independent. So when I say, and then we turn the next bottle cap over to see if we won, you have to say, well, did winning on the last bottle cap influence whether or not we win on this one? That's what independent means, that it would not influence it. And I'd say these are pretty independent trials of opening cans of soda or bottles of soda, because the next bottle cap and we win on the next is not going to care about if we win or lose. Now we say and we win on the next, and we win on the next, and we win on the next, and we win on the next. So we just go 2 more times right here. And what have I listed out? How many times in a row did we win? And what does this represent? How many times in a row did we win, and what does this represent? So this is what right here. This would be what, how many times? What does this represent right here mathematically? It's you win, and then you win, and then you win, and then you win. You just open all, you're like, oh, I'm a winner. I'm a winner again. I'm a winner again. Winner, winner, winner. Winner, winner, chicken dinner. So if you notice right here, this is what we just explained. So wouldn't the opposite side of it be the scenario of you lose on every bottle cap? So every bottle cap you twist off, this is you lose on all. You lost on the first, you lost on the second, you lost on the third, fourth, fifth, and sixth. But wait a minute. We don't want to see you lose on all of them. We want to see you win on at least one. This is where I get to draw on it. We don't want to see you lose on all the bottle caps. That's not what we're interested in. We want to see you win on at least one of them. So would you agree that either you lose on all the bottle caps, either all losers, so one of these things must occur 100% of the time, you'll have all losers or at least one winner. So either you'll have all losers or at least one winner. And guess what we can do here with this or? We can add them. Also, with all losers, we know the probability of all losers is this right here. So the probability of at least one winner, you got it, Wilson, great job, is just going to be, we can just take this, go over here, and subtract. And that's what I did. So either, and the plus can go away now, but this is what I did when I was thinking through it, that either they're all losers or there's at least one winner. And that's got it. That has the question. That is how we do it. Let's hop back. Ugh. Gotta wake up. And let's see. So we did that one, right? Yeah, we did. And this one's just a repeat. So check out earlier in the video. It's repeat. Repeat question. Traffic checks on a section of highway suggest that 85% of drivers are speeding. Oh, we did this one. It's that we can't multiply them together because they're not independent. It's another repeat question. This one right here we did. What other questions do you have? Because we've done all these. Try to see if there's a new one. We did this one to start. I think we've done all of them. We haven't done this one yet. This is the only one we haven't done. In a dresser, there are 10 blue shirts, 2 red shirts, and 4 black shirts. That's 16 shirts. What's the probability of a red shirt? 4 divided by 16, because there's 4 red shirts, 16 shirts. Don't worry, I promise I knew that. And what's the probability that a randomly selected shirt is not black? Oh, wait. 2 red shirts. Oh my gosh. 2 red shirts. And 4 blacks. So not black would be 75. Because there's black or not black. There we go. Can we do the car repair one? Yeah. Do you want to do the 2 car or the 1 car, Charlie? 2 car or 1 car repair? Yeah, exactly. The 2 car one's harder. The 2 car repair one is the harder version of it. So, yeah, that's the harder version. Okay. So you have to remember here, we're talking about 2 cars in this scenario. We're talking about 2 cars. And we have here that the probability of needing repairs is 17% for 1 repair. And this is just 1 car. It's not saying the probability 2 cars need 1 repair. It's saying you have a car. The probability a car of yours will need a repair is 17%. The probability your car will need 2 repairs this year is 8%. The probability your car this year will need 3 plus repairs, 3 or more repairs, is 2%. And you have 2 cars here. So this applies to both cars. This is the probability of either of your cars needing some sort of repairs. Now, what you can do with this problem to make it easier is you can look at this as the probability of needing some repair. What is the probability that your car will need some repair? So look at my problem here and tell me, what is the probability my car needs some repair? What is the probability one of my cars needs some sort of repair? 20. You are correct, Charlie. I had it wrong in my head. I thought, yeah, I did it wrong. Great job. That's why I paused. I was like, you're right. You're right. Excellent work, Charlie. 100 points. Good thing I didn't say it out loud what I was thinking because I was wrong. So the probability of repair, which means we just add them up, stop doing that, is 27%. And the probability of no repair would be what? Either our car needs some repair or our cars need no repairs would be what here? 73%. The probability of 27% was obtained by adding up the probability of 1, 2, 3 plus. Great job there, Nick. It's going to be either our car needs no repairs or our car needs some repairs. Now, one of the easiest ways to think about the problem is this way. We have 4 possible scenarios right here, so I'm solving it a little bit different of a way. Either the first car needs repairs and the second car needs repairs. Either the first car needs repairs and the second car does not need repairs. Either the first car does not need repairs and the second car needs repairs. And what is the only scenario I have not listed now? What is the only scenario I have not listed? It's because we have the first car needed repairs and the second car needed repairs. The first car needed repairs and the second car did not need repairs. No repair, no repair. Now you have to assume that these are independent. Decent assumption, but we can turn these all to mathematics. Independent means one of your cars needing repairs would not impact the other car needing repairs. And so we can turn them all into mathematics right here. Oh my gosh, what am I doing? So I'm just turning them into their formula numbers and failing at it a little bit. And last but not least. So these are all the things that could occur. So these are the probabilities, and these are the things that could occur, And now we just solve. And solving this out right here will actually solve the whole problem. And then we just have to understand in words what we're talking about. So there's that one. And then the next one is identical. But I'm just, oh my gosh. There we go. The next two are identical, I should say. And then 0.73 times 0.73. But you know what we could do? What's another way to solve for this one? Since this is everything that could occur, what's another way to solve for this one right now? Instead of solving that mathematics right there, what's another way to solve for this last probability? Which we should kind of know by this. Since this is everything that could occur, this is the sample space of what could occur. What's another way to solve for this probability right here? Which is a good check to make sure we know this. Subtract all of them from 1, exactly. Because it's going to be, these are the things, like if we say 1 minus all these other events, then we're just saying they don't occur. So we're just doing it the difficult way here. As long as I did the mathematics correctly, then this should be the answer right here. So hopefully I did it correctly. There you go. So because either one of these three occurs or this one occurs, they're complements. And every one of these is disjoint. So this is good review, Charlie, for what we were talking about last time, is that every single one of these is disjoint, but this set of three things is a complement to this one. Does that make sense there, Charlie, to say every single one of these is disjoint from the other one? Like either the first card needs repairs and the second card did not need repairs, or the first card needed repairs and the second card did not need repairs. These are disjoint, but the complement, wait, so which one is no more than one repair? I think you're doing the one car question, I think. Nick, I think you're doing the one car question. We'll do that one next here, Nick. We'll do that one next. I think you're doing the one car question. If you're doing the homework, look at the next question because it talks about one car and then this one talks about 2 cars. This is how to do the 2 car question. So let's sit here solving the 2 car question. Yeah, because this is the 2 car question. No, good question because they both use very similar stuff. And I'll do the 1 car question here in a second. So now that we have this all listed out, we actually have all the mathematics we need and we've solved the problem before we even started it. The probability that neither car will need repair is what? So neither car needing repair is going to be this one right here because this is no repair, no repair. Can I do this? I can almost do it. Look at that. Excellent. There we go. That's neither car needing repair. The probability that both will need repairs. So now we need to look at the probability both will need repairs, which is this one right here. There's probably both will need repairs. The probability at least one car will need repairs. So how could we do at least one car needs repairs? Well, either neither of our cars need repairs or at least one of our cars need repairs. So why don't we just take this number right here? Well, so remember, either neither of our cars will need repairs or, so here's neither of our cars need repairs or at least one of our cars will need repair. So there's 2 ways to do this. Because either neither of our cars will need repairs or at least one of our cars will need repairs. Oh, is it 3/4 of them need at least one repair? What is that? What does that say? Brian on Discord. So, not for this problem, not for this problem. For this, so what would we do here? No, okay, no worries, no worries. No worries, Charlie, you're doing excellent. But does it make sense that either this will happen? Here, I'll draw it the way I was doing it before. I'll draw on the coloring, that really helps. Where's my pens? So we're not interested in this. We are interested in this. So there's 2 ways to solve this. Because we want to see the probability that at least one of our cars will need repair. We've listed out the whole sample space of what could occur. So the 2 ways to solve it are that the sample space equals up to 1. So we could just subtract off the one event. But then also, these are all disjoint events. Since every one of these is a disjoint event, we could also add these up right here. Since they are all disjoint events, we can add them up. Because either we can say, well, then a car needing repair would be this or this or this. But we can also just subtract from 1 the probability of neither car needing repairs. So there's neither car need repairs, and there's at least one car need repairs. because either neither of our cars need repairs or at least one of our cars need repairs. Does that make sense, Charlie? That either neither of our cars will need repairs or at least one of our cars will need repairs. And we've shown this here visually by drawing it this way, that either neither of our cars need repairs, which is this probability, or at least one of our cars need repairs, which is the complement of neither cars need repairs. Yeah, so hopefully, I just hope seeing it visually helps and understanding how I'm using the addition rule right here because they're disjoint and using the multiplication rule down here because they're independent. It's either A or B, yeah. And then they're complements of each other because either, you have to say it's either this or this. They don't overlap and they encompass 100% of the probabilities. So they're complements because it must be A or it must be B, and they're disjoint because it can't be A or B at the same time, A and B at the same time. The other one is this one right here. This is very similar, but it's only dealing with one car. So now we're doing the one car problem. We need all these probabilities, 17, 5, and 3. Let's go ahead and take those over. Look at all this excellent work we did today. Great job, everybody. So probability of 1 is equal to 70%, 5%, 17, 5, and 3, I think it was. There we go. So we're missing one probability right here. We're missing one probability. We're missing the probability of 0, and we're going to do a quick check to make sure we have the correct thing right here. Let's make sure. There's always fuzz on the microphone. So I am hallucinating. So let's check those probabilities. 17, 5, and 3. We are correct. 17, 5, and 3. So with knowing that the probability a car needs 1 repair is 17%, probability 2 repairs is 5%, and probability of 3 plus repairs is 3%, we have now deduced 73%. If you're wondering how this was found, it's 100 minus 17 minus 5 minus 3, and it's just the, oh my gosh. Last problem, don't we? Yeah, wouldn't it be 75? I think I was talking about the 7s so much that I thought it was 7 and 3. And you're totally right, Charlie. Charlie, 100 points right there. That's why we check everything. That's why we make sure. It's always the simple math that's errors. You know, I can go and I can write 4 loops and get them to run. But if you ask me to do simple math, it's that darn subtraction. Man, that's tough stuff. It is so easy to make mistakes. So don't worry. Obviously, I make them too. So errors. Oh no, Mubot's not counting the errors. Let's put the errors back on. I always forget. I wish Mubot would do this. Oh no. There we go. Errors are now on right now. There we go. Oh my gosh. I cannot. These are errors right here. There we go. And so now the errors are increasing. So I have to click start on the counter, and then I always forget to, because when I boot up Mubot, he doesn't start with his counter on. I don't know why. I wish he could just default start the counter. And then some classes I'm getting things ready, and then I just don't go over to the counter thing to do start counter. I guess not everyone wants their counter going every. I don't mind Mubot. You can count my errors, Mubot. You good, Mubot? You good? See what Mubot has to say. Good. You must not fear Mubot. You know what's going on. So the probability that a car needs no repairs, we just solved this. The probability that a car needs no repairs is 75%, because it's the complement of the other ones right there. We'll get this a little bit better on the screen right here. There we go. Probability that a car needs no repairs is the complement of these remaining ones, we found out. And that would be 75%. Make sure to add properly. The probability that a car will need no more than 1 repair. So let's look visually what no more than 1 repair would look like. That is a car getting no more than 1 repair. So what's the probability that a car gets no more than 1 repair here? Because either it gets 0 repairs or, hey, Jessica, good to see you. We had someone here, I think they were mentioning Jessica's in the class. I think it was Victoria, right? They're like, I know Jessica. And I was like, I was like, yes. And so I think I know which one. If that sounds correct. If you have a question, feel free to ask. So we're about to finish up some probability right here. So we have 92% right here. 92%. Nice job. Yeah, that's awesome. So much positivity. Vols help Vols. I love the positivity. The probability that the car will get some repairs, either the car gets no repairs or it gets some repairs. So the probability, oh, you guys are great. I appreciate it. You made me blush. I appreciate it. I appreciate students helping each other out. Vols help Vols. It's, this is the craziest semester I've ever taught in. It's even crazier than last semester. I think one of the hardest things is the workload, because last semester everyone kind of, it's last semester we all kind of cut back on the work, and I think a lot of us are pushing more work this semester because the idea is, okay, since it's online, let's keep them more engaged. And I think unfortunately that has translated into more work. And then there's more hurdles because everyone's transitioning to online education. And the good news is a lot of my classes have not been restructured because I've been doing online education for 5 or 6 years. And that's, why I have stuff like this. And I'm really lucky that I have this. I say that all the time, that if I didn't have this, I can't imagine teaching via Zoom. It makes it for me to talk to everybody here. I bet there's going to be a lot of burnout with teachers. I don't say that I'm very distraught by that because teaching via Zoom is just not the same. This right here is much better to me. I still miss in-person teaching a lot. I still miss going into my classroom, seeing my students, saying hey to people, having people walk up and be like, hey, Brian, I've got this question, showing me their computer and be like, hey, take a look at this, take a look at this code. I miss that a lot. And so whenever I get back to campus, because the plan is I'm supposed to fly in. That was the plan, is I'd fly in once a month. And I was like, well, I'll be flying once a month. And I kind of like flying. I like hopping on a plane, taking a trip. And then I was going to stay with my department head, but current world situation, so the plan kind of got shaken up a little bit, but it'd be really fun and really cool if once a month I flew into Knoxville, spent a week in Knoxville, and I got to see my students. And then we'd also have the ability to stream online because we're building a mobile studio. So I'd still be streaming, but I'd be doing it from Knoxville. And then the plan was there'd be a classroom students could go to, and I'd teach them in person. So it's be 1/4 of the time I'd actually be teaching in person in Knoxville. So that was the original plan when this whole Brian teaching in Texas thing was thought up, and then the world changed, and it just coincided with me moving to Texas. I hope no one thinks I caused this. That's a huge joke. But it just coincided that, yeah. Oh, thank you, Nick. Thank you, Nick. I'm very interested to hear. I always want to know what people like and dislike. I'm very scatterbrained. I'm very ADD, and a lot of people like my randomness. A lot of people, and then some people are just like, I can't take this class. This guy's insane. But I want people to enjoy what they're learning. I want them to have some fun. And I treat this more like streaming than I do teaching. I mean, obviously I'm teaching, but we make some jokes. We talk about life every once in a while. Like right now we're completely distracted, but this is office hours. This is chill time. It's chill time. What if you have a problem, let me know. Like if there's a problem you're working on, but I think the adjustments have been hard for education, both on the students and on the teachers. And so it's really tough. Like I only know it from the teacher aspect now. I don't know it from the student aspect anymore. But I see the student aspect, and I definitely see from a lot of my colleagues and everything the faculty aspect. Could you, by chances being late if you haven't? Yeah, of course. Yeah, no problem. No, we're just chilling out. Don't worry about it. It's awesome. Say, hey, Brian, can you do this question? We got it. Let's see here. We're going to restart the quiz. Let's do that. We lost all our answers. Let's get the quiz going back here again. We always have to try to sympathize with people, try to understand the position they're coming from and their struggles. So I think, as faculty, it's important to us to try to understand the student experience of this brave new world. Quick question: what is your opinion on Halloween cookies? The Pillsbury ones, pumpkins or ghosts? Oh, I think which one? The Pillsbury. I'm gonna do that real quick. Question. Oh, he says yes. Pillsbury. The pumpkins or the ghosts? Let me look at them. Let me do this real quick. Pillsbury pumpkin cookies. Oh my gosh. And then there's the ghost ones. Hold on real quick. I'm totally going ghosts because it's got some UT orange on it. Totally going ghosts. I mean, no, pumpkins. What am I saying? Ghost got purple, and then he's a ghost. You never see the Pillsbury Doughboy as a ghost. That's kind of cool. Pumpkins just straight up Halloween though, and it makes me think of pumpkin spice. So I'm going pumpkin. It's UT orange, Halloween classic pumpkins. I mean, what you could go all Halloween without seeing. Oh no, Nick's saying ghosts. I think you could go all Halloween without seeing a ghost, both literal and everything. I You can't take the course, but I can answer questions. I'm more than happy to answer questions related to statistics. So good to have you here. So Kartik, so good to have you. Yeah, if you have a question, let me know, and I'll answer statistics questions. We're about to do another one with probability right here. But if you have a question, let me know. I know pumpkin spice is, oh man, pumpkin spice is life. Maybe Mubot. Is this the Mubot quote? Is this the Mubot quote? What's Mubot going to say? He needs those birthday cake flavored Cheetos. We need more quotes from Mubot. Let's do the train question right here. So we have a student figures out that they have a 10% chance of being let out late from class. You're welcome, Kartik. So good to see you here. So Stat Nation, totally up. And a student has a 10% chance of being let out late from class. If he leaves class late, there's a 16% chance he will miss his train. So think about this. You're going to have to miss class late and then, keyword, and then miss your train. So really there's two scenarios right here. And actually this one, due to the probabilities, is really nice to solve. Oh, you got it. You got it. You know it. You know it. You're just going to multiply them. I think it's right there. So there we go. You just multiply the two probabilities. Nice job, Nick. Figured it out right away. Because you get out of class late and then you miss your train. And that's it. Multiply the two probabilities. We got lucky it was 10%, which we can just move the decimal. Since it's 10%, if you remember the classic trick, you just move the decimal over. So I was like, okay, 16%, move it over to 0.016. And we have our rules of probabilities listed out right here. And this is the multiply. So wouldn't you say missing the train would be dependent on getting out of class late? It's treating it like it's a within probability. It's saying if you get out of class late, here's the probability of this. So you would need to get out of class late and then miss the train. It's not saying, here's what the problem is not saying. It's not saying you have a 16% chance of missing the train. It's saying you have a 16% chance of missing the train if you get out of class late. So you would need to get out of class late and then miss the train. Oh no, Nick. I'm so sorry to hear that, Nick. I'm so sorry. We've got here, I'll show you one more thing about that problem. So it says the probability, we've got three scenarios. You're either on time. So the probability of getting out on time from class is 90%. You get out of class late and you miss the train. Or you could get out of class late and not miss the train. Okay. So we can multiply these out right here. And we just did miss the train one. And then this one right here, and we'll write out the rest of these, would be 0.084. So this is the set of everything that could occur because you will either get out of class on time. I guess you'll catch the train then. You'll get out of class late and miss the train. If you're wondering how we're solving for this, here is the mathematics for how to solve for it. And then here's the mathematics for the last one. So this is all the mathematics right here to solve for everything that could occur. And what do you notice about all of these probabilities right now? All of these probabilities add up to what right here? Since we've listed the sample space of everything that could occur, every one of these, all the probabilities add up to 1 exactly. I think there's the one that asks about a bus being late for its stops. Can you do that one? Is there a bus being late to its stops? Can you copy part of it, Charlie? That one does not ring a bell. The probability of a bus being late to its stops. This is the is it this one? Because that's the only one that sounds like it. That's traffic jams. I don't know the bus being late to the stops one. Oh no, I don't know it. And I don't know where it's at in here. I don't know. Is it there? Load. If you can tell me more about it. I don't see the bus being late to the stop one. Was it on the quiz or the homework? Because we did all the homework. Oh no, Nick, dude, we're doing the quiz right there. I'll have to look. There's a tiniest bit of water left. I don't see the bus. Are you talking about the student missing the train or missing the bus? Yeah, I don't see it. If you I could make up a question about a bus being late to its stops, but I don't know of the question on the quiz or the homework where a bus is late to its stops. Is it on the next set of assignment questions? I don't think that it doesn't ring a bell. If you copy part of the question, then I'll take a look. Let's see. You know what we could do? We could end. We'll see if people have more questions, but we could end with doing a question from the next set of questions. And then we are doing confidence rolls. Okay, cool. And then, man, there's some tough stuff coming up. It's stuff you can't guess. So let me go to a question that I want to show. Okay, here we go. This is a tougher question. So here is some new material. Let's do some new material quick. And I'm going to teach you some conditions. You ready? Here's what we need to know for class today. We're going to learn a little bit for class today. We need to know condition 1 is random. Condition 1 is random. Condition 2 is less than 10%, or 10% we call it. Condition 3, we pause before we do it. And then condition 3 is success failure, at least for this instance. And we'll go into the details on these today. So with these assumptions, we'll meet these conditions. We'll cover conditions so much that you'll get bored of them. We'll like condition 1, random. Condition 2, 10%. And I miss being in class because I'll have people yell it out. Like when I'm doing, I'm like, condition 1, and the people are like, random. And I'm like, condition 2, 10%. And so I'll make them say it, and they'll know it just like this. When they get to the test, condition 1, random. Condition 2, 10%. And then you pause, and then you do condition 3. So here's where we have to actually use the mathematics. Isn't there a third condition? Yep, it's success failure. So we pause on the third condition because the third condition is different depending on what we're doing. So the third condition here is success failure condition. There is no order to the conditions. It's just the first two repeat. So the third condition being success failure is for categorical data. So since we're asking, is a child nearsighted, that's a yes/no answer. And we need to see if there's at least 10 successes and at least 10 failures. And the way to check this here is that if we have 191 children and 10% are nearsighted, then we'd expect 19.1 to be nearsighted, and we'd expect 90% to not be nearsighted. And both of these have at least 10 successes and at least 10 failures. So this is how we check at least 10 successes, at least 10 failures right here. And that's what success failures is at least 10 successes, at least 10 failures. I wish they went into more detail. This question right here, we have to know a formula for. This formula is given to us on the test. So you get a formula sheet. The formula is that the sampling distribution of the sample proportion is normally distributed with a mean of the proportion and a standard deviation of P times Q over N square root. Gosh, this is like, when we get to this, I'm like, man, this is towards the end of the course now. We're over the middle bump of the course. P times Q over N square root. So what does this represent right here of the distribution? That is the what of the distribution. So it's saying when we select children to see if they are nearsighted from a sample, we'd expect to see on what this. This is the what of the distribution. If you were to select 191 children to see if they're nearsighted, this is the what of what you'd see. This is the what. Since it's in that position, I'll write out some notation below here. That's the what of what you'd expect to see. The mean, that's on average. So if 10% of children are nearsighted, what would you expect to see on average? If 10% of children are nearsighted, what would you expect to see on average? If 10% of children are nearsighted, what would you expect to see on average? So think about what we can do if we know the answer to this. If 10% of children are nearsighted, which is the true proportion, then what would you expect to see on average? If 10% of children are nearsighted, then if you took a sample, what would you expect to see? 10%. So that means the answer is either C or A. The answer is either C or A because it has 10% at the very center of the distribution. Now we need to figure out the what of the distribution. So now we're saying the variation. So now we need to figure out the standard deviation of the distribution. Now we need the standard deviation of the distribution, like how far out spread it is. So if you remember, it was 10%, so we can take our numbers and plug them in here. So let's go down here. The mean was 10%. And we need to do square root of 0.10 times 0.90 over 191. So that's the standard deviation. So the standard deviation is going to be, go right there. And here's the standard deviation, 0.90 times 0.10 divided by 1.91. And that is the standard deviation. That is the spread of the distribution. So now we take this, and I want you to look at this real quickly right here. How many standard deviations does this graphic go out? How many standard deviations? No, wrong, Brian. How many standard deviations does this graphic go out? How many, what is the number? Oh, P and Q. P is the proportion, Q is the complement. Good question right there, Charlie. P is the proportion, which is 0.10, and Q is the complement. So P was 10% and Q was 90%. Does that make sense that P is 10% and Q is 90%? So that's how we're able to do that right there. P is 10% and Q is 90%. I wonder if I can. I'm going to try something real quick right here. I don't think I did that. Sure. And so 3 standard deviations is how much we go out. So we're just going to take this, multiply it by 3 standard deviations. And now we're just going to take this, add it to 10%, and subtract it. And look, that rounds to 0.16. They need to carry their decimals. And 10% minus it. Talk to my peers and say, carry your decimals out. So this will be the answer right here. Now the next question asks, what percent of... Wait, did you see it? Do you get it? So what we do is, so here's P, and then Q is the complement, times Q, over the sample size, square root. And I just found the what for the distribution. So it's P times Q over N square root. So we do P, which is 10%, Q is its complement, over N, and then square root of it. So that is the what of the distribution. So what we do here is we times it by 3, so we can get this number right here. And we go up 3 standard deviations from the mean. Hey, Anisha, good to see you. You were in summer 474, right? Is that correct? I think so. Here, wait. We'll go back to, there we go. So good to see you. Hope everything's going well. Are you one of the, I think I know, 474 and everything? Yes. So good to see you. I hope your semester's going well. We're solving some sampling distribution questions right here. Yeah. No, it's awesome. My gosh. Gosh, it seems like summer was just yesterday. It's not yesterday anymore. And just no haircuts. The Leah haircut soon. Just someone came in, Aaron came in here earlier and he's like, your hair is getting crazy long. He didn't say it that way. He's like, I like the flow. So, great. That is awesome. So good to hear that. Why did I multiply by 3? For this graphic, it just shows that we're going out 3 standard deviations. 1, 2, 3. It's just the way they visualized it. You can't see that on there. 1, 2, 3. So they're going up and down 3 standard deviations. So right there, that is 3 standard deviations above the mean. So that's why when I did the math right here, I took the mean and I added to it 3 standard deviations. And I don't know why their rounding's off, but we take the mean and we add to it 3 standard deviations. And we can take the mean and we can subtract from it 3 standard deviations to obtain the lower number. Does that make sense right there, Charlie? How we can add and subtract 3 standard deviations to obtain these numbers? So yeah, you're just going up 1, 2, 3 standard deviations, going down 1, 2, 3 standard deviations. You don't always have to do this. It's just the reason we multiply is because this is 1 standard deviation. Whoops, that's weird. There we go. P times Q over N square root. That's 1 standard deviation. Oh, see you, Anisha. So good to see you here. So this is 1 standard deviation, which would be the distance right here. Like how far down this is. Does that make sense, Charlie? This is 1 standard deviation down. And then if we go 2, we would just times it by 2. And then if you go another one, that'd be 3 standard deviations down. So that's 3 standard deviations. Because I'd already gone 2, so I went another standard deviation. So if you're wondering, there was our original standard deviation, and there's 3 standard deviations. Is that, yeah, good questions. I love the questions. 100 points. Keep asking them. Yeah, so if we were to draw out all the numbers on here, I'll show you what this would look like. 2 seconds, class not over yet. If you were to draw out all the numbers, what you could do... So here's what you could do. You could... Was that still open? Ah, no. Didn't do it. So what you could do is you could go right here, put the mean of 10% and the standard deviation, and here's the numbers right here. So here is the distribution, but with all the numbers. So now, because it just doesn't label all the numbers. So this is the distribution with all the numbers, with the mean going up each standard deviation. And this is what we are talking about right here. It just doesn't show all the standard deviations going up. It already does 3. Since we're using 191 students, then well, what would we have here? We'd expect between 3.4% of the 191. So 3.4% of 191, that is 6.49, looks just like that. Up to 16% of the 191, that's up to 32. There we go. And it's the 3 standard deviations we would use right there. That's got it. So Charlie, let's do this one real quick. You ready? If 8% of people don't pay their bank loans on time, what percent of people in a sample of 300 would you expect to not pay their bank loans on time? If 8% of people don't pay their bank loans on time, what percent of people would you expect in a sample of 300 to not pay their bank loans on time? So if 8% of people don't pay their bank loans on time, what percent of people in a sample of 800 would you expect to not pay their bank loans on time? And these questions come down in notation practice. So we know that 8% of people don't pay their bank loans on time. So if we were to sample 300, what percent of people would you expect to not pay their bank loans on time? We know that 8% of people don't pay their bank loans on time. I might have lost Charlie here. Oh, no worries. Wait, just think about this. 8% of people like Taco Bell. If you sample people, what percent of people would you expect to see liking Taco Bell? 8% of people. Oh, that is correct. We'd expect 24, but what percent is 24 out of 300? What percent of 24 is out of 300 is it? What percent is 24 out of 300? We'd expect 24 people, but we'd expect what percent, what proportion? We'd expect 8%. So it's saying if 8% of people don't pay their bank loans on time, we'd expect 8% of people to not pay their bank loans on time. Do you remember that P times Q over N square root? P times Q over N square root? Well, Charlie, I need your help. What is Q here? P is 0.08. What is Q? P is 0.08. What is Q? P is 0.08. What is Q? Bingo, exactly. P times Q over N square root. 3 decimals. There we go. And now it says, are the conditions met? Reasonable assumptions. Good. Now it asks the hard question. What percent of the time would 9% of people not pay their loans on time? So when you think about this, we need to go to the David M. Lane website. We need to go over here and put in the mean of 80%, 8%. I divided by 300, which was N. P times Q over N square root. I'll show the math on that again. So it was P, which was this, times Q, which is this, divide by 300 square root. And that's why we obtained this number right here. Does that make sense? P times Q over N square root. So P was this. The complement is this. Divide by the sample size. And then square root. P times Q over N square root. And then that's the answer we have for the standard deviation, which is how far out it is. And then what's the only thing I need to change? It wants to say what's the percent of time that 9% of people won't pay their loans on time. All I need to change is this. And there's the answer. Should be about 26%. I got it really close. Should have guessed it. So there it is right there. And that's the answer. We have just completed, there's the answer. We've completed 40% of this assignment. That one's a little tricky. It's not so bad. We've completed 40% of this assignment. The center of the histogram, the shape of the histogram becomes more normal. Decreases. There we go. 60% done. In the last 10 minutes or so, 60% done. Simulations will show reality. And we're talking about what happens to the mean and what happens to the standard deviation. So, and this should be the proportion right here. So you can see the distribution becoming more and more normal. So it's actually because of the success failure condition. But I think that's got it. So Charlie, did this help out? This next chapter, of course, is dealing with, we'll talk more about this today. I'll see you in class, and we're ready to go. I'll see if anyone else has some questions. Hopefully it's helped out a lot of people today. I'm sure we'll timestamp the videos, we'll put in what we're doing, and we'll help out. That's got it. I'll see everybody later. We'll Stats 1. I'll see you later. So bye for now. Bye, buddy.